as a math teacher. I mean, consider something. Consider. Consider is one of those words you say over and over again and your head ends up in the stars. Any C.S. Lewis fans get that one? As a math teacher. Floral tie looks fantastic. Good morning, good afternoon, good evening. Not sure what time it is where you are. Not even sure what I can call this math minute. I don't know if I can call it the Thursday math minute, the Friday math minute, or the Saturday math minute. Let's hit the median there. Let's presume this is going to be the Friday math minute. Welcome back. I hope you are well where you are. This is, of course, the only math minute guaranteed to be on Friday and guaranteed to be less than 10 minutes long. What I want to do today is finish up this series we've been doing on double distribution, or the area model for multiplication, or that annoying thing that my kid's teacher is making my kid do and I don't really understand. Whatever you call it is fine. I wanted to look at it because there's something kind of interesting to me. Again, this is a lot from my memory as a kid and my experience on social media as a math teacher. I mean, consider an example like 41 times 12. If we were going to do this with what we call the standard algorithm or the stacking algorithm, it would look like this, right? First, we would end up multiplying the 2 times the 1 and the 2 times the 4, and so that would give us 2. Obviously, 2 times 1 is 2, 2 times 4 is 8. And then, of course, we want to multiply the 1 times the 1 and the 1 times the 4. And we're moving over for a reason that perhaps we're starting to understand a little better, or maybe we're still not quite understanding why. We just remember we're supposed to do it. 1 times 1 is 1. 1 times 4 is 4. And we add all this up, and we get 492, right? Fortunately, no carries in that one. Fortunately, like I didn't choose the example on purpose. What your kid's teacher is making you learn stems from distribution. We've said several times now there are a couple different ways to think about this. You can do 41 times 12 is really the same thing as 41 times 10 plus 2. And when we look at it that way, hopefully you're realizing why we end up doing this placeholder thing, because we can see, 41 times 10, that is the 410. That was the second step of our stacking algorithm, or the second stage of our stacking algorithm. And then, of course, 41 times 2, that's 82. That was the first stage of our stacking algorithm. So the stacking algorithm is nothing more than the distributive property at work. And that's also why the addition ends up being involved in our multiplication. Now, that's not the fundamental reason. There's a more fundamental thing that's happening between addition and multiplication, but it's good enough for now. We can get into that in some future math minute. The reason I choose this example, though, is, again, maybe if you looked at that, you'd say, fine, whatever, but that's not what my kid's teacher is making me do. My kid's teacher is making me do this silly thing where we call 41 40 plus 1, we call 12 10 plus 2, and then the kid's teacher is talking about partial products or something. I'm having to fill in all these boxes, and then finally I'm having to add all this up. Why am I doing so much addition for math? Although I guess at the end of this process, I do get the same product, the same answer to multiplication, 492. The whole reason I wanted to look at this again today is that at least for me, when I see this on social media or I talk to people and I say, hey, I'm a math teacher, and this is one of the first complaints, why is my kid having to do this silly thing with the box? You hear a lot of negativity. And yet there's this other thing you see, and it's presented in a very different way. So let's take our multiplication. You can see, again, the standard algorithm still there, 41 times 12. Nothing changed magically in the last 30 seconds. It's still 492. But this thing I'm about to show you, when it pops up on local news or social media or whatever it might be, is not presented like, oh, look at this awful thing that my kid's teacher is making me do. It's presented like, oh my gosh, why don't they teach multiplication this way in schools? Here's what it looks like. Some people call this the Japanese method, the stick method. Google it. I don't know, all kinds of stuff. 41, let's think of as a little bit differently. We're not going to think of it as the numbers 4 and 1 or 40 plus 1 or anything like that. We're literally just going to draw 1, 2, 3, 4, and 1, right? So that's 41. I hope everybody can tell. And then 12, we're going to think of as a 1 and then a 2, right? 1 stick and 2 sticks, and that's 12. And what we want to pay attention to here are the intersections between our different lines or our different sticks. And so we bubble in all those intersections, and something interesting ends up happening. We kind of separate it out in a particular way, and we start looking at things, and we say, oh, okay, so there ended up being 4 intersections up here, and here in the middle there ended up being 9 intersections, right? And then down here at the bottom there ended up being 2 intersections, and oh my goodness, oh my gosh, 492 is the answer to that multiplication. What is going on here? How did the sticks know what the answer was to the 2-digit multiplication? I'll tell you what, the Japanese know how to teach math, don't they? Maybe they do, maybe they don't, but I do want you to see here, the 4, right? The 8, the 1, the 2, all of this we've seen already. The 4, the 8, the 1, the 2. This is the same thing as the area model that we're doing. In fact, it's arguably way better to do it in the area model than the sticks. So like I said, I carefully chose that example. And as long as all your digits remain relatively small, the Japanese method, the stick method, whatever you want to call it, it does end up working out really well. But let's think, instead of doing something where the numbers remain relatively small, let's consider like 93 times, let's do like 57, I guess. I'm not going to do the stacking algorithm this time. I just want to do the Japanese method, right? What would that end up looking like? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. So that's 93. And then 57, 1, 2, 3, oh, whoops, I ended up erasing. 4, 5, and oh my gosh, 1, 2, 3, 4, 5, 6, 7. And I've got to extend some of my lines now. Goodness. And now hold on a second. Wait. Where? Oh wait, was that 57? So like where do I end up drawing the U now? Like not quite so simple anymore. Wait, where did all those beautiful little dots and intersections go? How many of them were there? And my Japanese stick method, not looking so great with 93 times 57. But without jumping to the stacking algorithm, let's see what the box would have to say. 90 times 50, maybe not the easiest thing to do in the world, but 9 times 5, hopefully everybody remembers, 4,500. 50 times 3, 150. 90 times 7, 630. 7 times 3, 21. And as I write these partial products down, I do have some carrying I have to do. I'm not trying to tell you that this algorithm completely gets rid of carrying, but I just have the 1 there. 5, 3, 8, plus 2 makes 10, carry another 1. 1 and 5 and 1 makes 7, plus 6 makes 13, carry another 1. And so I get a product of 5,301. It's possible to do this with the Japanese method. I'm not trying to tell you it's not. I think this was 9 and 5. This would be 45 different intersections, or maybe I flipped that around. And then there would be... No, I think I did flip that around. I think the 45 intersections would be up here, 63 intersections over here, 15 intersections over here, and then there'd be 21 intersections down here. Now, I do want you to notice, oh my goodness, 45 intersections, you say, 15 intersections, 63 intersections, 21. The area model is actually a much more efficient way to represent this multiplication without having to draw all these different lines. Maybe it's going to be more efficient, maybe not, than the stacking, but it is the same thing as the stacking. 3 times 7 is 21, carry a 2. We're just carrying earlier in the process. 7 times 9 is 63, plus the 2 makes 65. We move one space over because we know we're looking at 50, not just 5. 5 times 3, of course, is 15. Carry another 1 up here. 5 times 9 is 45, plus the 1 makes 46. And then we add all this together, 1. 5 and 5 is 10 with a carry. 6 and 6 is 12 with a carry, 13. 1 and 4 is 5. And of course, we get 5,301 either way we do it. I'm not trying to tell you have to multiply any particular way. Teach your kid whatever way you want to teach. A good math teacher is going to deal with it no matter what. But I do want you to see these models aren't just coming from nowhere. They're not magic. They're just different ways to represent single-digit multiplications combined with place value. We're looking in the Japanese method with our hundreds, our tens, and our ones. Our hundreds, our tens, and our ones. Our hundreds, our tens, and our ones. These are all different ways to represent single-digit multiplications with place value. So hate on whichever of them that you want, love on whichever of them that you want, teach your kid whichever of them that you want, but just know the beautiful thing about mathematics is that it's systematic. So any method that works, any method that consistently delivers the right answer must have some system behind it that we can translate through different representations and different models. If it didn't, then it would be chaos. But chaos is something we're going to have to save for a different Math Minute. That has been your Friday Math Minute. I hope that is helpful to you. Show it to your kid, like, subscribe, send me some questions. I got other stuff I need to put in these Math Minutes. I can't just keep filling them up with math tricks. I mean, I could, but I'd prefer to do something that you send me. Have a great weekend.